Okay, all right. Happy Monday. Happy week 6. Week 6 Monday. Here we go. Okay, all right. Let's take a look. Today we will bring in the Bayes classifier. Okay. So we'll do some classification. So all of the other things, I mean, we haven't been done much. We did linear regression and neural networks. And the neural networks, even the ones where you were predicting a category, they were at the end of the day, the neural network outputs a number, right? The neural network outputs a number between 0 and 1, and you can set it up with kind of like, each category gets its own dummy variable, but we measure the difference between like 0.98 and 1 or something. We're doing that. This chapter, and so we are going to go to chapter 5 in our textbook. So chapter 4 is kind of like, I think, like the Bayesian approach, which is pretty cool, but it's not within the scope of our course. So we spent a lot of time in chapters 1 and 2, and now we're going to jump to chapter 5, which is on classification. And what we do in classification is the variable that we're trying to predict is a categorical variable, okay? And so our data coming in, okay, we have n observations. We call these our training objects. They exist in d dimensions, and each of them have some kind of categorical label, and that's going to be our target value, okay? Our target value. The classes or the categories that they can belong to, we use these numbers, but they're categories, okay? So, we have numbers 1, 2, up to letter C, okay? And these are the classes that our objects can belong to. And the goal is, if some new observation, x new, comes in, we can correctly predict the class that it belongs to, okay? And so, again, while the class labels are integers, we have to treat them as categories. So it does not make sense to try to predict a class label of 2.5 or 2.6. Those have no meaning, okay? You can only predict 1 or 2. And the label, number 4 is not twice as big as the label number 2. There's no kind of size comparison or something like that. You either get it right or you get it wrong, which is, that's one of the reasons why when we did the neural network for predicting categories, you have to create dummy variables. Why couldn't, we did the handwritten digits thing, right? So when we predict the handwritten digit, why couldn't we just predict the number 0 through 9? Why couldn't we just do that? Why couldn't we just have one node in the output, and that node just went predicted from 0 through 9, rather than having 10 nodes where each node was 0, the next node was 1, the next node was 2, the next node was 3. Any idea? So for the neural network to predict the 10 different digits, 0 through 9, we needed 10 nodes, because if we had one node, okay, and we predicted just a number between 0 and 9, what that would do is, let's say the true value was 8, and we predicted 7, okay? Then our error is 1, okay? But if the true value is 8 and we predicted a 2, then our error would be 6, okay? And we would say the 7 is less wrong than the 2, right? If you have a numeric output and you only have one node, and you're going to say, well, let's predict 0 through 9. If the true value is 8 and you predict a 7 versus a 2, the 7 is less wrong than the 2, okay? That makes sense if it's like you're trying to predict like how much money you have, If you actually have $8 and you predicted 7, yeah, you're closer to the answer than if you predicted 2. But when it's predicting something like what digit it is, it's either it's right or it's wrong. Okay? If you predict a 7, that's wrong. It's not less it's not less wrong than a 2. They're equally wrong. And so that's why we needed 10 separate nodes where everything's a 0 or a 1. Okay? And so similarly, whenever you do classification, you can't say like, oh, okay, well, the true category is 5 and we predicted 4, that's less wrong. No, it's you either get the category right or you don't. Today's classifier is going to be the Bayes classifier. And it's called the Bayes classifier because it uses Bayes' rule to find the probability that an observation belongs to a certain class. It's a probabilistic classifier. And so what it's going to do is it's going to return basically a vector of probabilities and you'll get a probability for each of the possible classes. So if there's 3 possible classes, and we'll just call them class A, class B, and class C, you'll get a vector of 3 values that add up to 1. So it'd be like A has probability 9.19, and B has probability 0.8, and C has probability 0.01, or something like that. So you get three different values that add up to 1. Another example of a probabilistic classifier is logistic regression. Logistic regression is useful for classifying things in 2 categories, a yes or a no, and you get a value between 0 and 1, and then your no will be 1 minus that value. Okay. There are also non-probabilistic classifiers, or we might call them hard classifiers, and they just say our model belongs to class B, and that's it. And there's no kind of probability associated with that. K-nearest neighbors is the original K-nearest neighbors is non-probabilistic. You can modify K-nearest neighbors a little bit to make it a little bit probabilistic too. We also have support vector machines, which is just it sounds fancy, but it's just let's draw a line. That's the classifier, and basically if you're on one side of the line, you get you're in this class, and if you're on the other side, you're in the other class. Okay, it uses Bayes' rule, and we call it the Bayesian classifier, but it's not considered to be Bayesian statistics. That's an entirely different thing. And I wrote it's covered in 102C, but and I wish I could teach 102C, but alas, it's not in the cards. Okay. All right. So anyway, this is Bayes' rule. We learned this. I don't know when we learned this. Stats 10, maybe. Also, 100A is like, it's a big deal, right? Okay, and it's you have this conditional probability, this given business, right? A probability of A given B is equal to the probability of A and B, or the intersection of A and B in the numerator, which can also be found by doing probability of B given A times the probability of A, and then we divide that by the probability of B. The denominator, probability of B, can be decomposed into the product of probability of B given A times the probability of A for all possible values of A, okay? And so the denominator is actually the numerator for all possible, it's the sum of the numerator for all possible categories of A. All right, let's go through an example, and we'll set it up for a classifier. So what we want the probability that the label for our new observation is class C, okay? And we're going to calculate that probability given the values in our X values in our new observation, along with all of the training data. The training data X and the training data T, so because we're saying we're using our training data to figure this thing out. So what has to happen is that the resulting probability has to be some number between 0 and 1. Obviously, it's a probability. Okay, and then if we were to calculate this resulting probability for all of the different classes, so if we have class A, B, and C, again, all of the probabilities have to add up to 1. Okay, so I mean, these are all just things that kind of make sense to us, but it's good to kind of explicitly write them out, so we can always kind of check our own work at the end of the day and just say, hey, does this make sense, right? So if somewhere along the way you're getting a value greater than 1, okay, we know we did something wrong. And if we get a bunch of values but they don't add up to 1, we also know we did something wrong. Okay, so our formulas just get more and more complicated, but it's really just Bayes' rule, right? So just keep in mind we have A given B is equal to B given A times the probability of A divided by the probability of B. Okay, this part, what's the probability that that it belongs to class C? That's like the A, and then this stuff is like the probability of B. Okay, so we're gonna say what is the probability that we belong to class C given our X values? It's equal to the probability of getting our X values if it does belong to class C. Okay, so what's the probability of getting the X values that we have if it belongs to class C? We multiply that by what's the probability that something belongs to class C regardless of the values, okay? And then we divide that by what's the probability of getting our X values regardless of what class it belongs to, okay? We like to use these names for the different pieces. Okay, the part that we're trying to figure out, this is our posterior. That's the probability we want to find. It's the probability that we belong to class C. Is there 80% chance we're in class C, or is it a 2% chance we're in class C? Okay, this part over here, this is the likelihood. It's the probability of getting the values that we have in X if we assumed it belonged to class C, right? So what is the probability that someone is over 6 feet tall if they are a man versus what's the probability that someone's over 6 feet tall if they are a woman? And those probabilities are different, right? The prior probability, okay, is just what's the probability that some new observation belongs to class C before we know anything else about it. So with that, regardless of what kind of X value we see, okay, so regardless, like even if we don't know anything about the person's height, okay, or whatever it is, what's the probability, the person is, a certain gender or something, okay, or whatever classification we're talking about. And then the marginal is just what's the probability of getting this X value regardless of whichever class they belong to. Okay, let me give you your first view quiz answer for today. Week 6, Monday. First answer is the letter C. C. C as in cat. Okay, what we will do is we can expand the denominator, the probability that we get some value X new, okay, or all the values in X, okay. We want to know what's the probability of getting, the values in our new observation, and regardless of what class it is, this is really just the sum of the probability of getting these X values if we sum it across all possible classes. What's the probability of getting our X value if we belong to class 1? What's the probability of getting these X values if we're in class 2? What's the probability of getting our X values if we belong to class 3? So on and so forth. And we add them all up, okay? And so, we go through all the possible values of, I guess, C prime from 1 to big C. And we add this up. So we're going to expand our denominator that way. Okay, we're going to try out this silly example of the Bayes classifier. Hopefully it makes sense. All right, so whatever, you go shopping online and you can buy whatever you want to buy, right? And you decide, I'm going to buy some marbles, okay? And you buy these pouches, okay? The pouches come with red marbles and blue marbles. And you decide, I'm going to buy 25 of these bags of marbles, okay? And I don't know, the bags are filled at 3 different factories, and each of these factories have slightly different red and blue mixing proportions, okay? And so 24, we get 25 pouches, 24 of them are labeled, okay? Half of them came from factory A, and then a quarter of them came from factory B, and a quarter of them came from factory C. So we're going to say 12 from factory A, 6 from B, and 6 from C. The last one's not labeled, and we're going to try to guess what factory that it came from, okay? And we're going to assume the bags, when they are filled at the factory, it's via some kind of, it's just a random thing. I don't know, you just mix red and blue marbles and they just dump them in, okay? So you got 25 bags here. This is our training data, and then we got our one that we're trying to figure out. Okay, all right, and so you decide to count all of the marbles that you have, and you look at, and you say, okay, well, we know these ones came from factory A, and you go through and you count how many red marbles you have, how many blue marbles you have for the ones that came from factory A, and it seems like in factory A, overall, 60% of the marbles are red, 40% are blue, okay? And then when you go to the bags that came from factory B, half of them, 50% are red and 50% are blue. And then when you look at the bags that came from factory C, you get 40% red and 60% blue, okay? Now, we don't work at the factories. We don't know the exact filling proportions. And when you open up the bags, they're not exactly, every single bag isn't exactly 60% red and 40% blue, right? Some might be like 62% red, and some might be 55% red, but overall, you're getting something around 60% red. So, right? So I wrote, one pouch from factory A has 20 marbles, and maybe it's 70% red, and then another a pouch from factory A has 20 marbles, and it's 55% red. Okay, so this is fine, and there's nothing in here that violates our assumption that they're filled by some kind of Bernoulli process, right? We're not getting a pouch from factory A that's 100% blue or something like that, because that would be kind of worrying for us that it's not following a Bernoulli process to fill it up. Okay, and so anyway, this is what we have. Okay, and then we look at our last bag, right? We open the last bag, and we open it up, and there's 20 marbles in there, and 10 of them are red, right? So it's 50% red, 50% blue in this bag. Okay, so now we want to know, given this information about the 3 different factories and their filling proportions, what's the probability that this bag came from factory A? What's the probability it came from factory B? What's the probability it came from factory C? Okay, so here we're going to start off with the likelihood. The likelihood is, what is the probability of getting the data that we have, the X values that we have in our data, if it came from factory A, or if it came from factory B, or if it came from factory C? Okay, this we can just use a binomial probability. Okay, so we can say with the getting 10, so when you calculate a likelihood, the X values are fixed and the parameters are what change. We're going to say, okay, the likelihood that it came from factory A, okay, is going to be 20 choose 10. Factory A has a filling proportion of 60% red, so we're going to do 0.6 to the 10, 0.4 to the 10, and we get 0.117. Okay, factory B is 50% red. Okay, so we do 20 choose 10, 0.5 to the 10, 0.5 to the 10, and we get 0.176. And then factory C is 40% red, and remember we got 10 out of 20 red, so we do 20 choose 10, 0.4 to the 10, 0.6 to the 10, we get 0.117, same as factory A there. So that's the likelihood of getting 10 red if you have a filling proportion of 60%, 10 red if you have filling proportion of 50%, and 10 red if you have filling proportion of 40%. Okay? All right, does that kind of make sense for getting our likelihood values? Okay. The prior probabilities, so remember, the formula is, the filling, probability that we're calculating, we have the likelihood, which we just did using binomial, and we're going to multiply that by our prior probability, and then we're going to divide by our what we call our marginal. Okay, so our prior probabilities is before we even opened up the bag. So prior to opening the bag, prior to looking at the x values, what is the probability that it came from a particular factory? Okay, so here we're going to make the assumption that when we got our shipment and half of our bags came from factory A, we're going to assume that factory A is responsible for half of all marble production for this, company or something like that. Okay, I don't know. Is that maybe that's not a good assumption, but that's what we're going to kind of assume. Okay, and because in our shipment, a quarter of our bags came from factory B, we're going to assume factory B is responsible for a quarter of the production, and then same with kind of factory C. So that's what we're going to do. We're going to say because of the proportion of the rest of our training data, we're going to assume factory A, the probability that came from factory A is just 0.5, probability that came from factory B is 0.25, and the probability that came from factory C is 0.25. This is just based on kind of prior to looking at the data, right? And so now what we want to do is we want to kind of balance these prior probabilities with our likelihoods, okay? And to do that, all we do is we just multiply them together. So we're going to calculate the numerator, okay, which is the likelihood times our prior. We just take the likelihood number from which we calculated using binomial, and we multiply it by the prior probability, which we calculated by just kind of doing a proportion of our things. Okay, so is that all right? So the numerator for class A is 0.058. The numerator for class B is 0.044, and the numerator for class C is 0.029. Okay, and so the likelihood for class A and the likelihood for class C are the same. It's what's the likelihood of getting 10 red out of 20 marbles if you have a filling proportion of 60% red versus a filling proportion of 40% red. Both of those produce the same likelihood. Okay. However, class A has kind of an advantage using the prior probabilities because when we looked at all of the bags, half of them came from factory A versus only a quarter of them came from factory C. So when you kind of multiply those two together, the numerator for class A ends up twice as big. Okay, so we have that. So these are basically kind of the three numbers that we have for our numerators, but in order to kind of turn them into a probability, we have to scale these up so all three probabilities add up to 1. Oops. Right? So if I say, okay, basically, if these are proportional to our answers, how do I scale these up so all three add up to 1? Okay, all you do is you would add these up, okay, and then you would divide each number by the sum, right? So that's all we're going to do. That's what that marginal probability is. Okay, we just add these three numbers up, and we get the sum, and then we're going to divide each of these numbers by that sum, and that's going to scale everything up so they add up to 1. Okay, and so that's all we do. Right? So this marginal probability is we take the numerator, we add them up across all possible classes. We've got 3 of them. And then so, those numerator values are 0.0585, 0.044, and 0.0292. So I take those values, 0.0585, 0.044, 0.0292, and then I get 0.1319, okay? And then I'm going to take all of each of these numbers and divide by 0.1319, okay? So that's the law of total probability. That's what we call it, right? And where we just say, all right, we're going to find the kind of the combined probability, but we do it for all of the different possible things. We say, okay, what is it for class A? What's the class for B, class C? And we add them up, and we say, okay, this is what we get, and then we're going to divide each number. So for class A, our numerator was 0.05857. We divide by that sum, which was 0.1319, and we get right around 0.444. Okay, 0.444, so around 4/9. Okay, and again, kind of the breakdown is we have the likelihood of our data multiplied by the prior probability divided by the marginal. So what is the probability that our bag belongs to class A if inside the bag we have 10 red out of 20 marbles, given all of the other training data is found by doing, okay, what we have is 10 red out of 20, so we say, what is the probability of getting 10 red if it came from class A, okay, multiplied by what's the prior probability that it came from class A, and then we divide by the marginal probability, which is the probability of getting 10 red regardless of which factory it came from, okay? And so this, the denominator is the sum of the numerators across all possible classes, which is 0.1319, and then the numerator in our case for class A is 0.0585. Okay, we do the same thing for class B and class C, all right? To get our numerator for class B, we say, well, what's the probability of getting 10 red out of 20 marbles if it comes from class B? Class B has a filling proportion of 0.5, so we have the binomial probability there. Factory B is responsible for a quarter of marble production there, so we get 0.334, and then for class C we get 0.222. All right, so these are the numbers that we get. So it's not exactly 4/9, 1/3, and 2/9, but it's pretty close to that. And so those are our kind of ending probabilities, all right? So what is the probability that it came from class A is 0.444. What's the probability it came from class B is around 0.33. And probability it came from class C is 0.222. So to just kind of put this back into context, our test case is 50% red, okay? And so if we were to look only at this information, that our bag was 50% red, kind of our maximum likelihood estimate would be factory B, because when we looked at all of our data, in fact, factory B had a filling proportion of 50% red, right? So we'd go, oh, our bag's 50% red, then it's got to come from factory B, which is 50% red, okay? And factory A was 60% red and factory C was 40% red, okay? But with the Bayes classifier, we don't just take into account kind of the likelihood of our data, but we also take into account this extra information that, first of all, factory A kind of produces half the bags and factory B only produces a quarter of the bags. So how do we weigh that, okay? So, when we do the likelihood, we say, okay, well, you know what? Getting 50% red in the bag, if it comes from factory A, is not that weird, right? Factory A has a filling proportion of 60% red. Getting only 10 out of 20 red in the bag is not that weird. So when we combine them, factory A still ends up the most probable class at 0.44. Okay, but it is a little bit lower than the prior probability, right? So prior to opening up the bag, factory A was in the lead with a 50% probability. After we open up the bag and we see that it's only 10 red out of 20 marbles, our probability drops down a little bit from 0.5 to 0.44, okay? Factory B and factory C started off with 0.25 probabilities prior to opening up the bag. After we opened up the bag, factory B gained some ground, right? It started off at 25%. After opening up the bag and taking into account the data that we saw, where we got 10 out of 20 red marbles, which matches factory B, it gained ground and went from 0.25 to 0.33, whereas factory C lost a little bit of ground going from 0.25 to 0.22, okay? There are some major assumptions that we made going into this model. All right, so let's keep that in mind, and at any time you can kind of change some of these assumptions and make some adjustments, right? So after tallying all the data in our training cases, we assumed that the kind of maximum likelihood estimates in our training data are kind of are reflective of what's happening at the factory. Okay. You can relax that if you take a fully Bayesian approach, but we're not going to do that in our class. Okay. And then the other kind of big assumption we made was that, well, we got 24 bags here, and because half of our bags came from factory A, we're also assuming that factory A is responsible for half of all marble production, okay? So we're assuming that our sample is representative of the class proportions in the population. Now, if you have more information, you might want to change your prior probabilities. So, for example, if you are like at the marble factory or marble company and you go, oh, you know what, factory A, B, and C all have the same marble production output, okay? We can say, our prior probabilities are 1/3 for each of these things, okay? And so you can say, prior to looking at your data, everything has a prior probability of 1/3, and you could ignore kind of the proportions in your training data. But you would need to have that kind of literally prior information, right? So you would need to have some kind of outside source that tells you that, and that that depends on your kind of domain knowledge, and I guess past research and stuff. I've given you one answer so far. Okay, your second answer today is the letter B. B as in bear. B. Okay, so just real quickly, what if we took another bag, okay, and it has 20 marbles in it, and only 6 of them are red, okay? So in this bag, it's only 30% red, okay? So now, what's the likelihood that it came from factory A? The likelihood it came from factory A is really, really small, right? Factory A is assumed to have a 60% filling proportion, so then for that bag, or that factory to produce a bag with only 6 red marbles is really low likelihood, okay? Factory B has a fairly low likelihood, but not as low. We're assuming a 0.5 probability or 0.5 filling proportion red. And then factory C, which we assume has a 0.4 filling proportion, has the highest likelihood of the 3 factories, okay? But even its likelihood isn't super high because, again, we're only getting 30% red, and it has a filling proportion of 0.4. But of the 3 factories, this one has the kind of highest likelihood, okay? And so when we add them up, our denominators, again, so these are our three values, and then this is still scaled in with the kind of prior probabilities of 0.5, 0.25, and 0.25. Again, we know our answers should be proportional to this, but we need to scale them up so they add up to 1. So we're going to divide by the sum of these values. We're going to put in 0.04277 in our denominator, and we get the posterior probabilities. What's the probability that it belongs to class A is only around 5 or 6%. Class B has around 21, 22%, and class C has something around 72, 73%. So in this case, if you have a bag of 20 marbles and only 6 of them are red, then class C is the most kind of probable factory that filled them, okay? Just because class C has a filling proportion of 0.4, and if you take that into account, you say, okay, this is the most likely thing to produce a bag that only has 30% red marbles, okay? Now, could it come from class A? It could, okay? But our probability that it came from class A is only around 6%. Okay, is that all right? So this is kind of the Bayes classifier. All right, and then I have some text there. So what we want to do is we're going to apply our Bayes classifier, but we're going to do it with the multivariate normal or multivariate Gaussian distribution. Okay, so remember this is just the PDF of the multivariate normal distribution, and thankfully on our computer there's a function, there's a library called MV norm, and then or is it MVT norm? I forget. It's either MV or MVT norm, multivariate norm, and then we have a function. Find the density of the multivariate norm, DMV norm, or something like that. it's okay. The library is MVT norm. And okay, so what I'm going to do is I'm going to just simulate some data. All right. And so MVT norm has a function to simulate random values from the multivariate norm, and that's our MV norm. It's the same thing as just using D norm and R norm and stuff like that, but now we just throw in MV and we get multivariate things, right? And then so to kind of generate your values, you need to have I'm going to just generate two-dimensional data. So my mean is a vector of 2. So I've got 3 classes: class A, class B, and class C. Class A has a mean of 2, 3. Class B has a mean of 0, 0. And class C has a mean of 2, -2. So just imagine this, right? 2, 3, 0, 0, and 2, -2. And then in our for class A, we have a matrix 3, 0, 0, 1. Okay, so there's x1 and x2 are independent. We have zeros in the off diagonals, and x1 has more variance than x2. Class B, we have the identity matrix for the thing. So they're basically 2 standard normal distributions, kind of, joint. And then class C, there is some covariance. We have covariance of 2.5, 2.5, and variance of 3, 3. Okay, so and I'm going to just generate 30 values from each of these classes. I'm going to combine them all into one big matrix X. All right, and this code is just so I can plot ellipses to kind of give me some contour lines, and I drew ellipses at I don't know, the 0.4, 0.65, 0.8, 0.9, and 0.95, I guess, density lines. Okay, which are a little bit are just arbitrary choices here, but this is kind of what our densities look like. Okay, so these are the true density lines. Okay, so centered. This one is centered at 0, 0, and this is exactly I don't know, variance of 1 and 1. Okay, and this one's centered at exactly 2, -2, and this one's centered at 2, 3. And then and I colored the points based on which class that they were generated from. Okay, and then so we're going to say, like, okay, if I pick this dot out here, what class did it come from? If I pick this dot out here, what class did it come from? And some of these, there's some overlap between some of these things. Okay, so I generated this data, so I know exactly the properties of the different distributions that generated this thing. But when you're working with classification data, you don't know. You don't know what the properties of each of these things are. Okay, you do know there are labels. Okay, your training data has the values and their labels. So we do know that we have blue dots and red dots and green dots, or class A and class B and class C. But what we got to do is we're going to have to estimate what is the mean of each of these things, what's the variance covariance of variance covariance matrices of each of these distributions. And so we're going to estimate those. Okay, estimating the mean, I think, is rather straightforward. The maximum likelihood estimate for the mean of a multivariate normal distribution is just the mean. You add up basically all of your x1 values, and then you take the mean of x1. You add up all of your x2 values. You take the mean of x2, and that's going to be what you have. Okay, so you're going to add up all of your x values for all the you take all of the observations that belong to class, whichever class you're looking at, class C here. You add up all of the observations that belong to class C. You divide by how many observations you have in class C. Okay. So here I'm going to just say, okay, take all the observations at XA and take the mean and X, and so the true center was 2, 3, and so because of random variation, we're not getting exactly 2, 3. We get something kind of close to that, but not exactly that. The true mean for class B was 0, 0, and we get something kind of close, but not exactly that. And the true mean for class C was 2, -2, and we get something kind of close, but not exactly that. okay, because we just generated 30 random points for each of these things. Okay, the maximum likelihood estimate for the variance is technically this, x minus mu times x minus mu transpose, summed up. Okay, so this would give you a 2 by 2 matrix, and you add this up and you divide by n over c. To kind of make it unbiased though, this is the maximum likelihood estimate. To make it unbiased, we'll divide by nc minus 1, okay? And if we do x minus mu transpose times x minus mu, this will give us basically the sum, the sum already, our 2 by 2 thing, okay? So we're going to just divide by n minus c 1. And this is easy for us to do because if you give R a matrix, okay, with a whole bunch of, our matrix is 30 rows, 2 columns, okay, and if you just say, hey, calculate the variance of that matrix, it's going to calculate exactly this, okay? It's going to give you a 2 by 2 matrix, okay? So I think our original, the matrix we used to generate our data was 3, 0, 0, 1, and, again, something kind of close, but not exactly that, right? And then this was the original data to generate this matrix was the identity 1, 0, 0, 1, and again, something kind of close, but not exactly that. And then this one ends up, I think, the most off, but that's, again, just a product of the random data. And I think we had 3, 2.5, 2.53, and we get, 2.2, 1.5, and 1.9. But that's what we have. Okay, so here I'm going to plot ellipses of our estimated distributions. Okay, so here the center is not exactly 0, 0, and they're not exactly concentric circles. They're slightly askew, reflecting that so these are the kind of the ellipses fit to our data. So they fit our data really well. Okay, and I think on this one I compare the original. So the lines that we use to generate it show up in black, and we can see, okay, so these lines fit our data pretty well versus like the original. Okay, we can see our data, seems like they came reasonably from these things. These are the ones that like we told RMV norm to use to generate it, but we can see, this doesn't fit it perfectly, whereas, these ones are estimates of our distributions based on the labeled data that we have, right? So we have to use our estimated things because we don't know the actual original distributions. Okay, so once we have these things, we go through the process and we can run the Bayes classifier. And so I'm running out of time. I guess this was from the previous quarter. I timed it to kind of get us there. But basically, we're going to put in a test case. So I'm going to have a test case at 0, 0. And this is really easy. Okay? And I say, all right, so if you have a test case at 0, 0, what class would you label it? All right? And this would be, okay, that's for sure going to be blue, right? But, we'll go through and we'll calculate the probabilities. And to do that, we just use the Bayes classifier. We say, okay, what is the likelihood that this distribution, the red distribution, generates the point 0, 0? And we say, okay, you know what? It's pretty unlikely to generate that value, okay? What's the likelihood that the blue distribution generates 0, 0? We go, okay, high likelihood, okay? And what's the likelihood that the green distribution generates 0, 0? Also very unlikely, okay? And so that goes into our likelihood values. The prior probabilities, in this case, all three classes have equal representation, so our prior probabilities will just be 1/3, and then and so those will kind of eventually cancel out, but we'll include them in our calculations, and then we just scale all of the values up so everything adds up to 1. Okay, and so we'll take a look and we'll continue this on Wednesday, and then we'll relax some assumptions. Or I guess not relax assumptions, we'll actually make even more assumptions to simplify our life, and you look at the naive Bayes classifier. So this is the Bayes classifier. If we add a few more assumptions that make it more incorrect, but make our life easier, we'll have the naive Bayes classifier. So we'll take a look at that on Wednesday. Okay, let me give you your last view quiz answer for today, which is the letter E. E as in elephant. E as in elephant. And we'll end there. Okay, all right. Well, have a great rest of your Monday, and we'll see you Wednesday.